Well, today is day 3 of our online series on field forces. It's Wednesday, March 18th, and we're going to be talking about having you guys determine the mass and weight of an apple on the moon and Earth. So we're talking about the difference between mass and weight. So a couple days ago we talked about force of gravity in different places in space. Like a guy standing on Earth is 9.8 meters per second square for the acceleration. This guy in the middle of nowhere, in the middle of empty space, was 0 acceleration because there's nothing pulling on him. And then the sun, this guy standing on the sun had the most acceleration of gravity because the sun, I think you figured out, because the sun is so huge and it's pulling a whole lot on him. Let's talk a second about this on the moon right here. Acceleration on the moon, 1.6 meters per second squared. We actually did go to the moon. We have some videos, evidence, for example, of astronauts on the moon, and you can see them bouncing around, jumping around, and there's this crazy thing online where people are saying, hey, we never went to the moon, and how the shadows are all off and things like that. If you look at this video, these videos right here, I want you to notice these videos were taken in the late 60s, 1960s, right? And if you look at space movies back at that time, they actually didn't have the technology in Hollywood to make these special effects, right? If you look at these guys jumping around, this is not just slow motion video. This is not people just jump around in the desert with slow motion videos like that one that fell off his backpack, for example, that he's going to go pick up now, that rock right there that fell off. And they're bouncing around, the dust in the air, that is being pulled down by gravity. 1.6 meters per second squared. It's the motion. You can measure that acceleration just by looking at doing analysis of the falling of the objects on the screen. And you don't just fake that by slowing it down. If it's that easy to do, then you can do special effects of people in space. But you can't do that. So this is not only is it showing acceleration of gravity being smaller on the moon, but it also helps us with evidence that we did actually go to the moon. So what we're going to be talking about is weight versus mass. Let me show you this CD-ROM.
The mass of an object depends on the amount of matter the object contains. As long as the amount of matter remains constant, so does the mass of the object. The weight of an object depends on the force gravity exerts on it. Therefore, if the force of gravity on an object changes, so does its weight.
So there's a difference between mass and weight, and this will show you in measurements.
The weight of an object depends on gravity. Changing an object's location will change its weight. For example, consider an astronaut who has a mass of 80 kilograms. On Earth, this astronaut weighs 784 newtons, but on the moon's surface, where the force of gravity is only 1.6 meters per second squared, the astronaut weighs 131 newtons. The astronaut's mass, however, remains the same on Earth or the moon.
So we can see when we compare these are all 4 different things. First, the mass on the right, the mass of this astronaut is 80 kilograms on Earth and 80 kilograms on the moon. The mass stays the same because the astronaut is made out of 80 kilograms of stuff. But over here, when you look at the weight, the astronaut's weight is 84 newtons, but his weight on the moon is only 131 newtons on the moon. The weight changes because the object that's pulling down on him changes.
Weight can be measured using a spring scale. The spring scale measures the force exerted on an object by gravity. The weight of an object is expressed in newtons.
So this is, you can tell the difference between weight and mass by what we use to measure them. All right, we use a spring scale. So a spring scale is a spring, and when you pull on it, it stretches the spring farther and farther, and then there's a little lines on the side, and you can measure how many lines down it pulls. So for example, this mass hanging here on the end of the spring scale, when you hold it above Earth, it pulls the spring down, and it might measure, it might weigh, it might show a weight of 6 newtons when it pulls down when it's above the Earth, because the Earth is pulling down on this mass and stretches the spring to 6 newtons. Now, if I take the exact same thing, if I take this and somehow bring it over to the moon, okay, you'll notice something different. The moon is, what do you think will happen when I bring this to the moon? What happens to the spring when I bring this over to the moon now? What happens to the spring? And so what happens to the measurement of the force of gravity pulling on the spring when it's above the moon? What kind of measurement do you think you're going to get for the weight of this object on the moon? So the spring over here pulls not as far because the moon is smaller, so it has less mass, and it pulls less on this and makes the spring not stretch as much. So it's actually about 1/6. So it'll be about 1/6 of the weight on the moon. So the weight on the Earth is 6 newtons. The weight on the moon would be about 1 newton, because you can see it's going to stretch the spring less on the moon and more on the Earth. So you can think of weight in terms of how we measure it with a spring scale, and that pulls it down. The object's pulling down on different amounts, so it makes different weights. Now let's talk about mass.
Mass is measured using a balance. A balance uses a comparative mass on a lever arm to determine the mass of an object. The mass of an object is expressed in kilograms.
Okay, so mass. Mass uses a balance. So here's weight. Let's go to mass. You can make a balance, basically like a teeter-totter, an arm on a pivot point like this. And if you have some object, you can stick it on one end over here. I'll put this purple box on the left side. And then you just put masses on the right side until it balances out. That's why it's called a balance. So for example, if I put 5 kilograms here on this side and it makes it level, that means that this box has a mass of 5 kilograms. So I can take this and put it here over the Earth and get the mass of the object is 5 kilograms. Now, what if I were to take this entire thing and bring it over above the moon? Okay, so if I bring this over to the moon, the exact same object, exact same arm, exact same pivot point, but now how much mass do you think I'm going to have to put above right here on this side to make this balance out? How many kilograms would I have to put on? When it was above the moon, Earth, I had to put 5 kilograms. Above the moon, how much mass do you think I'm going to have to put to make it balance? Well, it's actually going to be 5 kilograms still, right? Because the thing is, the force is pulling on the left side and the right side with the same amount of force because it's still above the moon. Even though the force over here pulled down more, the force pulled this side more, even though the Earth is pulling more. The left side is also pulling on the right side. So this is why when you use a balance, it pulls both sides. The object itself pulling at the moon or the Earth, the effect of the moon or the Earth is the same on both sides of the object. So it ends up being the same amount of measurement, whether or not you have it above the Earth or the moon. 5 kilograms in the moon, 5 kilograms over Earth. So the mass stays the same no matter where you measure it in space because of the way we measure mass, for example. It's the same amount of stuff, 5 kilograms of stuff in the box. So here's my little memorization aid for this. Mass is really simple. Mass is just mass. It's the kilograms. It's just how much stuff is made out of kilograms. It never changes. Wherever you move it, it's the same amount of mass. Okay? Matter of fact, it's called inertia, the inertia of an object. So inertia of the elephant, for example, has the same inertia no matter where you put inertia of the elephant. Inertia of the elephant can be falling, standing, can be on Earth, on the moon, has the same amount of stuff that the elephant is made out of, same amount of stuff, same amount of kilograms. Now, weight. If I ask you about weight, right, the weight you measure with a spring scale. When I ask you weight, you question weight, weight, weight. You say wait because you want to stop. Wait, stop, calculate, wait, calculate. To get the weight, you have to calculate the weight with our equation, right? Weight equals mass times little g, which is 9.8. So my memorization is weight, calculate. How do you get your weight? Mass times 9.8. So that's the difference. To help you remember, mass is just mass, kilograms, done. Weight, calculate. Mass times 9.8 on Earth. So let's try this. So our equation is right here. Weight is m times g, right? And little g is 9.8. Let's finish up today with an example. Turn to page 42. And basically, you're going to be copying the blue, for this one example problem. This is warm-up 1. It's our first warm-up for this unit. On Earth, what is the mass of a 0.1 kilogram apple? And then what is the weight of the apple on Earth? Mass equals, so you're gonna fill it in there, and then the weight. Weight, calculate, right? You get the force of gravity. So you some letter times g. You plug in the two numbers and you calculate the weight. After you copy this down, the question is, how much mass does this 0.1 kilogram apple have? Mass is just mass. It's the kilograms of stuff that the apple's made out of. So it is going to be 0.1 kilograms. That's it. End story. Now the weight, if you calculate, look at your formula sheet or look at your notes from earlier this week. The weight is equal to something times little g. What letter goes right here? It is m. M times g. Weight, calculate. How do you get your weight? Mass times... Now you plug them in here. You plug in the m. You plug in the little g. Then you calculate it. And you get your answer. So what two numbers go in here? Okay, so the mass is right there, 0.1, and then little g is 9.8. And then you calculate them, 9.8 times 0.1. It's 0.98. And then what's the units for the weight? Remember, weight is measured, it's the force of gravity. So what do we measure the weight in? Newtons is force. Okay, we want to finish up doing this again, but with the same apple on the moon. So let's move this apple to the moon. On the moon, the acceleration of gravity on the moon is 1/6 of Earth's gravity. So what's the mass and the weight of the same apple from up here on the moon? We're going to use some of the same stuff, but now it's on the moon. So first, let's do the mass. What is the mass of this apple when it's on the moon? Okay, remember, mass is just mass. It's just the kilograms. So you just write down the kilograms. The mass is going to be the 0.1 kilograms. Mass is just mass. It's the same as before. Mass is just mass. The apple's still made out of the same amount of stuff. Now let's do the weight of this apple. The weight. Weight, calculate. So now we have to use our equation. The force of gravity is mass times little g, except now we know something. The gravity on the moon, so what are we going to put here for this fraction? Right, it's 1/6. The moon's gravity is 1/6 of Earth's gravity, so it's going to be smaller. So we have to 1/6 of what we did before for the equation for the weight. So now we plug in the 1/6, and then what two numbers are you going to plug in here? You're going to plug in the mass, 0.1, and then little g, 9.8. And you multiply this all together. And again, for the weight, we're going to get newtons. And then you put in your calculator, and you end up getting 0.163 newtons. Okay? So there you go. The force of gravity on Earth, the weight was 0.98 newtons, and the weight on the moon was 1/6 of that. And then the mass of the apple on Earth was the same as the mass of the apple on the moon, 0.1 kilograms.